Hey everyone, welcome. If you're staring down the barrel of the PPD or PDD exams for the ARE, then you have landed in exactly the right place. Today we're going to break down one of the trickiest topics in architectural acoustics, the absorption coefficient. Let's just dive right in.
I want you to picture something we've all experienced. You're standing in the middle of a huge, empty school gym. Someone claps their hands, someone else bounces a basketball, and the sound just explodes, right? It becomes this long, muddy, chaotic echo. So why does that happen? Why is it that some rooms feel acoustically comfortable and clear, while others are just a total sonic nightmare? Well, it all comes down to a constant battle happening between the materials in that room and the sound energy flying around.
To get our heads around this, let's think about it in a super simple way. We're going to imagine that every single material in a room is either a sound mirror or a sound sponge. It's the simple clash between reflecting sound and absorbing it that's really at the heart of everything.
And this is where our main character enters the story, the absorption coefficient. We use the Greek letter alpha for it, and honestly, it's just a simple score. It's a grade that tells us exactly how spongy a material is. It measures what fraction of the sound gets soaked up versus what fraction bounces right off.
So, in one corner, you've got your sound mirrors. These are the hard, dense, reflective surfaces like concrete, glass, or even a polished marble floor. They just bounce sound all over the place. And in the other corner, you have the sound sponges, soft, porous things like thick carpets, heavy drapes, or those acoustic ceiling tiles that are really good at just eating up sound.
And the scale we use for this is super simple. It just runs from 0 to 1. So a material with a score of 0 is a perfect sound mirror. It reflects 100% of the sound that hits it. And a material with a score of 1.0, that's a perfect sound sponge. It absorbs absolutely everything. Of course, in the real world, pretty much everything falls somewhere in the middle.
Okay, let's put some real numbers to this. Check out marble. Its alpha is just 0.01. That is a textbook sound mirror. Now look at heavy curtains over on the other end, 0.75. That's a pretty good sponge. And then you've got something like an acoustic tile with a whopping 0.95. That's a super sponge, basically. These are the materials you use when you really want to kill that echo in a room.
All right, that seems pretty straightforward, right? A simple number from 0 to 1. Well, hold on. This next part is where it gets a little more interesting, and it's where the ARE loves to trip people up. That absorption coefficient, it's not actually just one single number.
You see, a material's sponginess isn't one size fits all. It actually changes depending on the pitch of the sound hitting it. So, a material can be an amazing sponge for high-pitched sounds, but act like a total mirror for low-pitched sounds. This is a critical concept for the exam, so you've got to lock this down.
So check this out. Let's look at something super common, like carpet laid over a concrete slab. Down at 125 Hz, that's a deep, low, bassy sound. The carpet is basically useless. Its alpha is only 0.08. It's a mirror. But watch what happens as the pitch goes up into the range of human speech, around 1,000 or 2,000 Hz, the alpha shoots up to over 0.70. The carpet suddenly becomes a really good sponge.
And this chart, man, it just lays it all out for you, doesn't it? You can see it right there. The bars on the left, for the low frequencies, are tiny. The bars on the right, for the higher frequencies, are huge. So what's the big takeaway? It's crucial. Carpet is fantastic for soaking up high-pitched office chatter, but it's going to do almost nothing for the thumping bass from the nightclub next door.
Okay, so you might be thinking, if this number changes for every single frequency, how on earth are we supposed to compare two materials? Great question. And the answer is a little shortcut architects and acousticians use, called the noise reduction coefficient, or NRC.
The NRC is basically a simplified single number rating. It's designed to give you a quick, general idea of how a material performs. And this, you might want to write this down for the exam, it's calculated by averaging the absorption coefficients at 4 very specific frequencies, the ones most important for understanding speech, 250, 500, 1000, and 2000 Hz.
And you'll see this all the time on manufacturers' websites or in their spec sheets. Here's a data sheet for an acoustic product. You see all the different alpha values for all the different frequencies, and then, right there at the end, is the NRC. It's that quick, at-a-glance number that lets you compare products easily, especially for spaces where people are talking.
So, the big question is, when is NRC our best friend? And when does it when does it hide the truth from us? It's really useful for quick comparisons for spaces like offices, classrooms, conference rooms, anywhere speech is the main sound. But And this is a huge but. It has a major blind spot. Because it focuses on speech, it completely ignores what's happening at those low bass frequencies. You would never, ever rely just on NRC to design a concert hall or a movie theater.
Okay, everybody lean in. We have reached what I think is the #1 trap on the ARE when it comes to acoustics. This is the big point of confusion, and if you can master this, you're going to be in great shape. First up, we've got absorption. This is everything we've been talking about, measured by alpha and summarized by NRC. Its whole job, its entire reason for being, is to manage the sound quality inside a single room. It's about soaking up echoes to make things clearer. Think room acoustics.
And then there's this other thing, which is totally different. Isolation. This is all about stopping sound from getting from one room to another. We measure this with something called STC, or sound transmission class. This has nothing to do with echo. It's all about blocking sound. This is what we mean when we say soundproofing.
Let me say this as clearly as I possibly can, because this is the point. Absorption fixes the sound in a room. Isolation blocks the sound between rooms. That fluffy acoustic panel with a high NRC does practically nothing to stop your voice from getting to the next room. And that heavy concrete wall with a high STC rating, it'll stop sound dead, but it can create a horrible echo inside the room. Mixing these two up is the classic exam mistake. Don't let it happen to you.
Ooh, okay. That was a lot, I know. So let's boil it all down into a super simple cheat sheet that you can use for your final review.
Seriously, if you're going to remember one thing from this whole talk, make it this slide. Screenshot it, write it down, whatever you need to do. Let's run through it. Alpha is the sound sponge score from 0 to 1. The higher the alpha, the less echo. The key detail, it's always frequency dependent. NRC is just a simple average for speech, good for quick comparisons. And the big one, the exam trap. Absorption is for inside a room. Isolation is for between rooms. You get this, you're golden.
So let's go all the way back to the beginning. That huge, echoing gem. Now you understand the difference between sound mirrors and sound sponges. You know that frequency is a game changer. And you know what NRC can and can't tell you. So, how would you start to fix that space? You're the architect. What's your first move? What materials are you specifying, and where are you going to put them? Think about it. You've got this.